Hello, to another episode, in my channel Learn with Jarvis, and before we begin please subscribe. A neutron star is the collapsed core of a giant star which before collapse had a total mass of between 10 and 29 solar masses. Neutron stars are the smallest and densest stars, excluding black holes, hypothetical white holes, quark stars and strange stars. Neutron stars have a radius on the order of 10 kilometers (6.2 miles) and a mass of about 1.4 solar masses. They result from the supernova explosion of a massive star, combined with gravitational collapse, that compresses the core past white dwarf star density to that of atomic nuclei. Once formed, they no longer actively generate heat, and cool over time. However, they may still evolve further through collision or accretion. Most of the basic models for these objects imply that neutron stars are composed almost entirely of neutron subatomic particles with no net electrical charge and with slightly larger mass than protons. The electrons and protons present in normal matter combine to produce neutrons at the conditions in a neutron star. Neutron stars are partially supported against further collapse by neutron degeneracy pressure, a phenomenon described by the Pauli exclusion principle, just as white dwarfs are supported against collapse by electron degeneracy pressure. However, neutron degeneracy pressure is not by itself sufficient to hold up an object beyond 0.7 m, and repulsive nuclear forces play a larger role in supporting more massive neutron stars. If the remnant star has a mass exceeding the Tolman-Penheimer-Volkoff limit of around 2 solar masses, the combination of degeneracy pressure and nuclear forces is insufficient to support the neutron star and it continues collapsing to form a black hole. Neutron stars that can be observed are very hot and typically have a surface temperature of around 600,000 kelvins. They are so dense that a normal-size matchbox containing neutron star material would have a weight of approximately 3 billion tons, the same weight as a 0.5 cubic kilometer chunk of the Earth, a cube with edges of about 800 meters from Earth's surface. Their magnetic fields are between 108 and 10^15 100 million to 1 quadrillion times stronger than Earth's magnetic field. The gravitational field at the neutron star's surface is about 200 billion times that of Earth's gravitational field. As the star's core collapses, its rotation rate increases as a result of conservation of angular momentum, hence newly formed neutron stars rotate at up to several hundred times per second. Some neutron stars emit beams of electromagnetic radiation that make them detectable as pulsars. Indeed, the discovery of pulsars by Jocelyn Bell Bernal and Antony Hewish in 1967 was the first observational suggestion that neutron stars exist. The radiation from pulsars is thought to be primarily emitted from regions near the magnetic poles. If the magnetic poles do not coincide with the rotational axis of the neutron star, the emission beam will sweep the sky, and when seen from a distance, if the observer is somewhere in the path of the beam, it will appear as pulses of radiation coming from a fixed point in space, the so-called lighthouse effect. The fastest spinning neutron star known is PSRJ 1748-2446 AD, rotating at a rate of 716 times a second or 43,000 revolutions per minute, giving a linear speed at the surface on the order of 0.24 c, that is nearly a quarter the speed of light. There are thought to be around 100 million neutron stars in the Milky Way, a figure obtained by estimating the number of stars that have undergone supernova explosions. However, most are old and cold, and neutron stars can only be easily detected in certain instances, such as if they are a pulsar or part of a binary system Y. Slow-rotating and non-accreting neutron stars are almost undetectable. However, since the Hubble Space Telescope detection of RxJ 185635-3754, a few nearby neutron stars that appear to emit only thermal radiation have been detected. Soft gamma repeaters are conjectured to be a type of neutron star with very strong magnetic fields, known as magnetars, or alternatively, neutron stars with fossil disks around them. And goodbye, to another episode in Learn with Jarvis. Hello.